All right, in chapter 9, we talked all about gases. So chapter 10 brings us to the other two common states of matter, right? Liquids and solids. And we're going to talk about the interactions of those liquids and solids, which do depend a lot on their chemical state. And the overarching theme of chapter 10, which is intermolecular forces, we'll see drives a lot of that activity. There will be 5 videos that are recorded for chapter 10, some a little bit longer, some shorter, right, as we break up the section or the chapter by section. And we're going to explore why things like water will go from ice water to liquid water to water vapor, right, in the gaseous form, whereas CO2, carbon dioxide, will go directly from the solid state to the gaseous state, right, a process called sublimation. Okay. So we've got 6 sections in chapter 10, right? Will correspond to 5 videos because we'll lump these two, 10.3 and 10.4 together into one video. Yeah. But let's talk about that idea I just introduced in this first video, 10.1, intermolecular forces, which you'll see me abbreviate commonly as IMFs. Okay, so IMFs are intermolecular forces. This is a term that's used even if something isn't a molecule. Okay? So intermolecular forces, not exclusive to molecules. You can see it for atoms as well, for example. Okay? But these intermolecular forces, or IMFs, are the various forces of attraction that can exist, right? May or may not exist between atoms and molecules of a substance due to electrostatic phenomena. Right, electrostatics, we talked about that before, positives and negatives, opposite charges being attracted to one another. Okay. And so the phase of something, solid, liquid, gas, right, depends on intermolecular forces and the kinetic energy of the particles, okay? Whether or not there's enough kinetic energy to overcome forces of attraction, because different substances have different states at different temperatures. Okay? So that's why, because everything has different IMFs, and that corresponds to the kinetic energy of their environment, right, controlling the state. So we know solids, liquids, and gases at this point, right? And as we increase the temperature, which is the kinetic energy, we go from solid to liquid to gas in most situations, right? However, the opposite is true for intermolecular forces. As you increase the extent of the intermolecular forces, you go from gas to liquid to solid. So that's a key idea if you're recording notes as we go through here, right? Kinetic energy and intermolecular forces have an opposite relationship. Okay. And that, as we're about to see, right, will control a lot of these states of matter and explain some phenomena you've already seen in your life. Okay. Take condensation, for example. Right? You see condensation all the time on the outside of a cold drink. Okay. That drink being cooler, right, having a lower temperature, a lower kinetic energy, slows these molecules down, okay, that encounter the outside of the glass in this situation. Slowing those particles down causes them to go from the gas phase to the liquid phase. Okay? And that's what causes condensation. We could also see that happen with high pressure. Right? Take a lighter, right? The inside of a lighter is butane. Now, if this was an open container, right, butane is actually in the gaseous form at room temperature. Okay? But having it under higher pressure in this situation, right, allows you to see it in the liquid form, right? And then you release small bits of gas that get ignited. Okay? So that's another situation. As you compress something, increase the pressure, you go from a gas to a liquid, and if there were a high enough pressure, you could even take it to the solid state in some situations. Okay. So again, the focus here is intermolecular forces. Okay. That means we're looking between molecules, either two of the same molecule, two different molecules, right? Intermolecular forces, it's between two things. That's different from an intramolecular force. That's something within a single molecule. Okay. That's forming like a covalent bond, for example. That's an intramolecular force. Chapter 10, we're thinking about intermolecular intermolecular forces. So make sure you're using that properly, because those things are an order of magnitude different from one another, right? Intramolecular forces are much stronger. And these intermolecular forces, the IMFs, as we've already said, determine their state, and they determine a lot of physical properties, though, as I just mentioned, they are not as strong as bonds. Now, the first term, and we're going to have 4 of them from this video that we need to know, right? So jot these down as we go through, our van der Waals forces. Van der Waals forces are the sum of all the attractive forces between neutral atoms and molecules. Okay, might be a lot, might be a little. Key thing is that they are neutral. So let's see what that looks like with an image, right? 2 neutral molecules of HCl here. Think about it as being in the gaseous state. An intramolecular force is a bond. Right? And those are much stronger than what we're talking about in chapter 10, which are intermolecular forces, or IMFs, which are weaker relative to bonds. And there are several types of intermolecular forces, and we're going to think about 3 of them, okay, from this video. The first one is called a London dispersion force, and this is the weakest of the 3 intermolecular forces, a London dispersion force. Okay. This is a force of attraction due to an instantaneous dipole. Okay. So it's something that exists for the spur of the moment. It's not permanent. This happens because electrons are in constant motion. If you can think about them as like water in a glass, if you're tilting it back and forth, like a wave of electrons. And what this can result in is, for a split second, there being, right, electron density at a higher part of a molecule than at a different part. Okay, so one end of the molecule would have a slight positive charge because the electrons have left. Another part of the molecule would have a slight negative charge where those electrons are existing. And when that happens, it triggers a response in other molecules, right? A partial positive, for example, in one molecule will attract electrons from a different molecule, right? That's called an induced dipole. So for a split second there, we get a weak electrostatic attraction between 2 molecules, right? Which is what this looks like right here. When you see that delta, we've talked about this before with Lewis structures, and in dipoles, that delta negative means a partial negative charge, delta positive means a partial positive, and they are temporary dipoles that are attracted to one another. Okay. And the larger the molecule, this is a key idea as well for London dispersion forces, the larger the molecule, the greater the extent of London dispersion forces, okay? Because it's a greater area, greater probability of getting that temporary dipole. So we see as things get heavier, their intermolecular forces get stronger, and that means things like their boiling point get higher. Okay, so size is important. Larger size, stronger IMFs, higher boiling point. But shape is important as well. If things have the same mass, for example, they're the same size, the shape is significant, because if something has a high degree of branching, that means it has a lower boiling point. Let's take a look at some molecules here, right? These are all isomers of pentane. Okay. But as we go from straight chain N-pentane to isopentane to neopentane, which have more branching, okay, same molecular weights, right? Just more branching. See how the increasing the degree of branching here, going from right to left, decreases the boiling point? It's because these things can't overlap as strongly with one another. Right? If it's in a straight line like that, those dipoles can get really close to one another because it's like just stacking 2 straight lines on top of one another. Okay? Whereas here, it's more like a circle, right? And if you try to put 2 circles on one another, they don't overlap to the same degree. And so increasing branching decreases intermolecular forces and thus decreases the boiling point. So that's intermolecular force number 1, London dispersion forces. What's number 2? Dipole-dipole attractions. Dipole-dipole IMFs are seen in polar molecules. You have to have a polar molecule. And it's kind of like a London dispersion force, except instead of having that temporary dipole, polar molecules have permanent dipoles, meaning they have a permanent partial positive and a permanent partial negative. And those things are attracted to one another all the time, the opposite charges, right? The negative dipole and the positive dipole. And they have that electrostatic attraction. That is a dipole-dipole force. So it looks pretty similar to what we saw before, right? But the difference is now it's permanent. Okay? So it's stronger because it exists all the time. So that's number 2, dipole-dipole. Number 3 is a specific subset of dipole. Okay? It's called hydrogen bonding. This is the strongest of the 3 intermolecular forces. Okay? And it's really significant because it's responsible for the special properties of water and life on Earth as we know it. Okay? This has the highest, most concentrated partial charges due to the small size of hydrogen. You see it right there in the name, hydrogen bonding. And there's only 3 situations where you'll have hydrogen bonding. It's when you have hydrogen that's directly bonded to oxygen, nitrogen, or fluorine. Okay. And that gives you a really large delta positive on hydrogen and a really large delta negative on oxygen. Right? It's these 3 because they're 3 of the most electronegative elements. Okay. So these bonds, these intermolecular forces, right, it's called hydrogen bonding. It is not actually a bond. It's called hydrogen bonding, but it's an intermolecular force. The strongest intermolecular force, still not as strong as a covalent bond would be. Okay. So here's an image of what hydrogen bonding looks like. Okay. The delta positive on hydrogen attracted to the delta negative on oxygen in water, for example. So if you see some exceptions in boiling points, like here on the graph, right? Previously, we said as these things get larger, they get higher boiling points, which is true, but nitrogen, fluorine, and oxygen are the smallest in those groups. They still have the highest boiling points because these guys have hydrogen bonding, which is the strongest IMF. These do not. And one small fun fact, right, before we end the video, hydrogen bonding is what's responsible for holding DNA together. Right, your nitrogenous bases, they're held together in the middle of the strand there by hydrogen bonding. And so that's what keeps your double helix wound together. So key ideas from this chapter. Okay? Know the 4 terms: van der Waals forces, London dispersion forces, dipole-dipole, hydrogen bonding. Know the criteria for each, know the weakest and the strongest. Okay? And we'll use those in the next video to continue talking about properties of liquids first, then phase transitions, and then we finish the chapter talking about solids.